The objective of this lecture is to provide the third part of the study of the orbit as a function of time. This lecture focuses on the development of a method for orbit propagation using Kepler's equation. This lecture is organized as follows. First, the overall structure is provided. For propagation on an elliptic orbit. And then, using that structure, we're going to develop a method for orbit propagation. And this method is going to involve a sequence of steps, but some of the key steps are going to involve conversions between position and velocity and orbital elements and perhaps the most important step is going to be the solution of Kepler's equation. So first, we will discuss the overall structure of orbit propagation. Now first, what is meant by orbit propagation? So orbit propagation means the following. Is to determine the position and velocity of a spacecraft on an orbit at some time t, and we'll just denote that as a general time t, given the position and velocity at some other time t0. Now, generally speaking, t is greater than t0 because we're moving forward on the orbit. But it need not be the case. We could actually be moving backward on the orbit to figure out what happened at an earlier time. But in this case, we're going to refer to everything as being moving forward on the orbit. So now, given that that's the definition of orbit propagation, here's what the structure looks like. Imagine we're on an elliptic orbit. So we're doing this whole thing for the case of an ellipse. So we have an elliptic orbit. And at some time, t0, the spacecraft is located at a point on the orbit. Now, I could label all these points as I did before. Here's the periapsis, here's the focus, here's the spacecraft at time t0. So this is time t0. Now, what do we know at time t0? Well, we know the position at t0, and we know the inertial velocity at t0. And at some later time, it could be any time, it doesn't matter what it is, I'll just arbitrarily put some point down here. This is time t. So at time t, we have that there's some position and velocity at this time too. So we know that we have some r at t and vi at t. Now, given that we've moved from t0 to t, we want to know, given the initial position and velocity and given the amount of time that we've moved on the orbit from t0 to t, in this case it's the time difference, t minus t0, what is the position and what is the inertial velocity at time t. So that's the question. So the objective is determine r at t and vi at t given r at t0 and vi at t0. So of course we also have to know the times, right? We have to know the initial time and the final time. So I'm assuming there that we know both of those as well. So that's the objective. So that's the overall structure. Now what we're going to do is we're going to provide a method for being able to compute the position and the inertial velocity at some later time t, given the position and the inertial velocity at some earlier time t0. So this is the method for orbit propagation. And it's going to use Kepler's equation. And we're going to assume that we are on an elliptic orbit. So that's the first assumption. So assume that the spacecraft is moving on an elliptic orbit. So if it's moving on an elliptic orbit, that immediately implies that the eccentricity has to be between 0 and strictly less than 1. It can't be a parabola and it can't be a hyperbola. We're not dealing with that particular case. Now, we need a few functions that we're going to refer to quite frequently in this derivation. Some of these are functions we've derived earlier. Some are just, I'm giving names to these functions that are methods that we derived earlier. So the key functions that we need are as follows. The first one is we need a function which is going to be called RV2OE. Now this function converts position and inertial velocity to classical orbital elements. Now the inputs to this function are r and vi, and also the gravitational parameter mu. The outputs of this function are the 6 classical orbital elements and they are A, E, omega, I, little omega, and nu. So those are the outputs. Now, that function plays a key role in the development of this method. The second function that we need is the inverse function, which is OE to RV. Now, this function converts the classical orbital elements to position and inertial velocity. So the inputs to this function are the classical orbital elements. So the 6 classical orbital elements, which we've already defined as A, E, omega, I, little omega, and nu. And we also need the gravitational parameter mu. The outputs of this function are R and VI. So the inverse outputs, right? The RV to OE goes from position and velocity to orbital elements. OE to RV goes the other way. So the way we're going to denote this, just to make things a little simpler, is we're going to use the following notation for these two functions. So the notation for RV to OE and OE to RV is as follows, is that we're going to say theta, we're going to call this thing theta, is equal to RV to OE of R, VI, and mu. So we're going to look at this like a function. The inputs are R, VI, and mu. The outputs are theta. And theta is this list of orbital elements. So we can see that theta has 6 elements, right? So this is going to be theta 1, theta 2, theta 3, theta 4, theta 5, and theta 6. Now, the inverse operation, which is OE to RV, is going to take the 6 classical orbital elements along with the gravitational parameter mu and produce back for me the position and the inertial velocity. So that's the notation that we're going to use. Whenever we say RV to OE, we mean what I've written here. Whenever we say OE to RV, it's the same thing. It's what I've written here. So I've written it kind of as in the form of a function, right? Or, a computer function, if you want to think of it that way. Now, the other functions that we need the third one, which is we need the relationship between E and nu. So remember that E is equal to 2 times the 4-quadrant inverse tangent of the square root of 1 minus E times the sine of nu over 2 and the square root of 1 plus E times the cosine of nu over 2. And that came from our derivation of the relationship between true anomaly and eccentric anomaly. And then, of course, we need the inverse operation, which is nu is equal to 2 times the 4-quadrant inverse tangent of the square root of 1 plus E times the sine of E over 2 and the square root of 1 minus E times the cosine of E over 2. Now, these functions are going to be used quite frequently in this in what we're about to do. So I wanted to lay them out ahead of time so that you know that they're coming. So you know that in steps that we're about to do, these functions will show up. And the last function that we need is something that is quite non-standard, but it's going to be denoted lower bracket x. What this function means is this is the smallest integer in x. So x is the input argument, and when I take the smallest integer in that, this is the notation that I'm going to use. So for example, if x is 4.5, well, the smallest integer in 4.5 is 4. If x is 7.2, the smallest integer in 7.2 is 7. And I'm going to need that result in the calculations that I'm about to do. So again, I'm defining it ahead of time so that we're not defining it in line when we're actually doing the method, because it'll get distracting if we're doing it at that point. So I'm trying to do this ahead of time. So this is going to be needed as well. So these are the basic functions that are going to be used in the method that follows. So next, we need to state clearly the information that is provided or the information that's given. So this is the given information. So we're given the position at time t0, the inertial velocity at time t0, the initial time t0 itself, and the end time, which is t. And it's also important to realize that the position and the velocity are expressed in Earth-centered inertial Cartesian coordinates. So r and vi are expressed in Earth-centered inertial Cartesian coordinates. And we'll just abbreviate Earth-centered inertial as ECI. So that's important. We're gonna have everything in Earth-centered inertial Cartesian coordinates. So here are the steps for orbit propagation. On an elliptic orbit. So the first step, which I'm going to label step 1, is convert r of t0, vi of t0 to orbital elements. So this step looks as follows, is that I'm going to call these initial set of orbital elements, I'm going to call them theta 0. It's equal to RV to OE, as I defined RV to OE earlier, and R of T0, VI of T0, and mu. And this conversion from position and velocity to orbital elements was a method that I had developed in a previous lecture when we did the relationship between position and velocity and orbital elements. So now theta 0 itself has 6 elements, right? So theta 0 is actually going to look as follows. It's going to look like A, E, omega, I, little omega, and nu 0. Now remember, the first 5 orbital elements are constant. The only orbital element that changes is nu. So nu 0 is the true anomaly associated with the position and velocity at the initial time. So nu 0 is the true anomaly at t0. Now that's going to be a key quantity that we're going to need in the future steps. The other 5 we need for later, but they're constant. They don't change. The only one that changes is nu 0 because it's the only thing that defines the location of the spacecraft on the orbit. So once we have nu 0, then we can go to step 2. So step 2 is to convert nu 0 to E0. So I'm going to get the initial eccentric anomaly. So the initial eccentric anomaly is equal to 2 times the 4-quadrant inverse tangent of the square root of 1 minus E times the sine of nu over 2, and this is nu 0 over 2, and then the square root of 1 plus E times the cosine of nu 0 over 2. So then we move on to step 3. So step 3 is to determine Tp, which is the time of periapsis passage just prior to T0. So in order to be able to determine that time, we have to work with Kepler's equation and be able to solve for Tp. So recall from Kepler's equation that E0 minus little e times the sine of E0, that's equal to the square root of mu over a cubed times T0 minus Tp. So as a result, we can solve this equation for Tp. So then T0 minus Tp is equal to the square root of a cubed over mu times E0 minus little e times the sine of E0. And that gives that Tp is equal to T0 minus the square root of a cubed over mu times E0 minus little e times the sine of E0. And you'll notice in this equation that we know T0 and we know E0 because we just computed E0 in the previous step. So now we know Tp. So we're done computing Tp. Now the next step is to determine K. Now you'll remember from the derivation of Kepler's equation that K is equal to the number of periapsis crossings en route from Tp to T. Now, in order to be able to compute that, we first need to compute the orbital period. So tau is equal to 2 pi times the square root of a cubed over mu, which is equal to the orbital period. Now, given the orbital period, we can actually compute k as follows. So k is actually equal to, now remember that smallest integer in x? Well, this is where it comes into play, which is that this is the smallest integer in t minus Tp all divided by tau. Now we know t, we know Tp because we just computed Tp in the previous step, and we know tau because we just computed tau. So as a result, we now have k, which is the number of periapsis crossings. And we're going to need that in the next step. So the next step is to determine the quantity which I had called C in Kepler's equation. Now C was defined as follows. The quantity C is defined as, well, if you recall, when I wrote Kepler's equation out, we had E minus little e times the sine of E was equal to C, where C is equal to the square root of mu over a cubed times t minus t0 minus 2 pi k plus E0 minus little e times the sine of E0. Now, that came from the fact that when I rearranged Kepler's equation, I actually got it in the form that I'm showing you here, where C is this big constant. Now let's look at this value C. You can see that it depends on mu, which we know. It depends on A, which we know because we computed it when we computed the orbital elements. It also depends on T and T0, both which we know. It depends on K, which we just computed in a previous step. And it depends on E0, which we also computed in a previous step. So everything in here can now be substituted. All those quantities can be substituted in order to compute C. And now we have the value of C. So we're done with this step. So the next step is to solve Kepler's equation. So when we rearrange Kepler's equation, we get E is equal to little e times the sine of E plus C. Now remember that E is between 0 and 1 and it can't equal 1. So what we're going to do is we're going to do a fixed point iteration. So fixed point iteration looks like this. Is that if we have a function of the form x equals f of x, then the fixed point iteration looks like xj plus 1 equals f of xj. That's the fixed point iteration. So this right here is the fixed point iteration. But in order to be able to do this fixed point iteration, we need to start with an initial guess. So what we're going to do is we're going to say let E equal E0 minus little e times the sine of E0. Now that actually happens to have a name, E0 minus little e times sine of E0. It's called the mean anomaly, but I'm not going to worry about that here. We may work with it a little bit more a little bit later. But that is the starting point. And then what we do is we do an iteration. And the iteration looks like this. For j equals 1 to capital J, where capital J is the number of iterations, I just say E is equal to E sine of E plus C, and then I end the iterations. And J, as I said, is equal to the number of iterations. Now, the number of iterations can be a little complicated because it depends on the value of E, E being the eccentricity. And so we're actually going to come up with a little formula here for how to determine the value of J. So the value of J, this capital J now, is determined as follows. Now we know that for small e, J should be smaller than for larger e. So whatever this thing is that we're going to do to determine J, it has to be such that as e gets bigger and bigger and gets closer to 1, it winds up giving us something that is a growing number. So what we're going to do is we're going to actually do this. We're going to say J is equal to 10 times, and it's going to be the log base 10 of 1 over 1 minus e. Now, that in and of itself doesn't exactly work. So what we're going to do is we're going to take the largest integer in that. Now, if you look at this, when e is 0, this gives you log base 10 of 1, which means you don't have to iterate, because when e is 0, you're on a circle, you're going to get the solution right away. But as e gets larger and larger, you can see that 1 over 1 minus e, as e approaches 1, goes to infinity. So as long as e is not 1, this quantity 1 over 1 minus e is going to be finite. And then I multiply it by 10 for a safety factor. And this notation that I've got here is the same notation I had for the smallest integer in x. This notation with the upper bracket, x, is equal to the largest integer in x. So what that means is that if, for some reason, the value of x in this argument is 10.4, it's going to go up to 11. If it's 21.2, it's going to go up to 22. It's going to give the next largest integer in whatever is in x. Instead of going down, it's going to go up. So it rounds towards positive infinity, if you want to call it that. So that's the way you compute J. And then you just run the iteration on a computer the way you would think. You just go for J equals 1 to capital J, and you just keep updating E, and when you're all done, you wind up having the value of E. So when we're done with this calculation, we have E. So after solving Kepler's equation, E is known. So then we move on to step 7. And step 7 is to convert E to nu. But we know that the equation that does that, I wrote it down earlier, is nu is equal to 2 times the inverse tangent of the square root of 1 plus e times the sine of the eccentric anomaly divided by 2, and the square root of 1 minus e times the cosine of the eccentric anomaly divided by 2. So in one step, we actually have the value of nu given the value of e, because we just computed the eccentric anomaly in the previous step by solving Kepler's equation. Then the next step is to assemble the orbital elements at t. So we know that theta, which is the set of orbital elements at t, is a, e, omega, I, little omega, and nu. Now that value of nu is the value of nu that I just computed in the 7th step. So we're going to use that now in the next step. So the next step is to convert the orbital elements at t to r at t and vi at t. Now that step is performed using the function OE to RV. So this step looks as follows. It's OE to RV of theta, which I just assembled in the previous step, and mu. So this function OE to RV is the one that I had derived earlier in steps. Given the orbital elements, how do you compute position and velocity? And then when I go through that sequence of steps, which is in this function that I've just given as sort of a high-level function, I now have all the information to be able to compute the position and the inertial velocity at time t. So steps 1 through 9 provide a process for determining r and vi at time t given r and vi at t0. And that's the entire process. We're going to go through steps 1 through 9. We're going to do all of those functions in the order in which I wrote them and get exactly the quantities that I got. And in the end, when we're all done, the last step is going to convert all the way back to position and velocity from orbital elements at the final point, and we're done. Now, you can see that in the process of doing this, what we've actually done is we've taken a 3-dimensional problem and we've projected it into a 2-dimensional problem and then moved ourselves back into 3 dimensions. So that's the key part of this, is that we start in 3 dimensions. So the process starts in 3 dimensions. With r at t0 and vi at t0. It then, the process moves to 2 dimensions when dealing with motion in the orbit plane. And once we're done with that, at the end, the process moves back to 3 dimensions to determine r of t and vi of t. So that's the entire procedure or method from beginning to end. And that takes us to the end of this lecture. So to summarize this lecture, first, we developed the overall structure for propagation on an elliptic orbit. And then we developed a method for orbit propagation that involved using Kepler's equation. And then at the end, we provided a brief overview of what really the steps meant, in terms of going from 3 dimensions to 2 dimensions and back to 3 dimensions. And that takes us to the end of this particular lecture. We're going to use this method to be able to do orbit propagation when we're actually doing things in the later material. So this material is going to be very important because this method needs to be eventually coded in a language that makes it possible to actually implement it in real code, because you're not going to do these calculations by hand. And we'll end this lecture here.